Great. So our next speaker of the day is Veronica Collazuol from CHL, and she will tell us about the twists at infinite distance in the CHL string. Please take it away.
Thank you very much. So first of all, I want to thank the organizers that invited me to speak here today. And I wanted to talk a bit about this business of affinization at infinite distance in moduli space. In the case of CHL string, which is the subject of this last paper I wrote with Ilarion Melnikov, building on the two previous works with Mariana, Alvaro, and Hector. According to the Swampland program, it is generally believed that at infinite distance in moduli spaces of string compactification, there are universal features arising which are independent on the kind of the compactification itself. So for example, according to the distance conjecture, going towards this limit, we expect to find a full tower of states becoming exponentially massless in the moduli space geodesic distance. And according to the emergent string conjectures, these towers are predicted to be in some duality frame, either Kaluza-Krain towers or a tower of string oscillators of a string which becomes asymptotically tensionless and critical. So if we focus, for instance, on this moduli space, which is, for example, the one of the heterotic string on a d-dimensional torus, we know that in the infinite distance limits that correspond to the compactification limit to a higher dimensional heterotic theory, we find some affine symmetry enhancements. So the algebras that we see in the theory are of affine type. And so one natural question is to understand whether these patterns are actually universal in the moduli space, in the sense that if we fix the theory we want to decompactify to, do these symmetries depend on the kind of component of the moduli space we start with or not? And then the first place to look at is still in the context of the heterotic theory, and in particular of heterotic orbifolds, where these algebras still arise, let's say, perturbatively, and they can be studied with worldsheet techniques. And in particular, we made the comparison between the heterotic string and the CHL string, which I will review briefly in the following, because it's known that they both share a decompactification limit from 9 to 10 dimension to the 10-dimensional heterotic E times CH string, but they have two different moduli spaces. And so we wanted to ask this question in this setting. So first of all, let me briefly review how to characterize these algebras in a generic point of moduli space. And for simplicity, let me do it in the heterotic case. So we focus on algebras arising in the left moving sector of the theory, because it's where the non-trivial symmetry enhancement takes place. And then if you want to understand these algebras that are generated by the gauge bosons corresponding to massless vectors in the string spectrum, we can equivalently study from the worldsheet point of view the set of holomorphic currents that are conserved and have conformal dimension 1, 0. At the generic point in the moduli space of our theory on d-dimensional torus, the symmetry is U1 to the d plus 16. But then there are special loci in the moduli space where there are additional currents of the global worldsheet symmetry that enhance the symmetry to a group G of rank R plus additional U1 factor in such a way that the rank of the theory is still d plus 16. These G's are of ADE type and are realized at level 1 on the worldsheet and have been nicely classified in this series of papers. In order to read explicitly the algebra G at a certain point, we can study the set of currents that are conserved there. And in particular, their OPE structure gives us some information about the algebra, and in particular, the double pole gives us the Cartan-Killing metric, while the single pole has information about the structure constants. Equivalently, we could also study this information, for instance, through correlators, where the Cartan-Killing metric is related to the 2-point correlator between the currents, where Z12 is just the difference Z1 minus Z2, while the structure constant is related to the 3-point function between currents. Okay, so this is a kind of a general tool that we can use also to study kind of the decompactification and infinite distance limits. So let's consider now like a theory on like a bigger dimensional torus. So let's consider a torus of d plus k dimensions and the corresponding moduli space. And let's choose a path that leads us to decompactifying k dimensions. And this can be done, for instance, considering k radii of the torus to go to infinity and tuning particular moduli of related to the TD. We can ask to end up in a higher dimensional theory, which has a symmetry given by the current J's, given by G times still these bunch of U1 factors, where the data are given by K and F. And in particular, we can still ask, let's say, from the lower dimensional point of view, so on M d plus k, what is the affine algebra that is seen in this limit? And in order to do this, we should characterize the worldsheet current that become conserved and holomorphic just in the limit of the path we follow. So this is a kind of looking for these conserved currents is kind of a statement that is independent on the specific path, provided that the final point is the same. And then we find that there are infinitely many currents in the limit that are given by the momentum tower of the finite of the currents of the finite higher dimensional algebra, where the NJs are the momenta along the x directions, which are the bosons that we decompactify. And in addition, there are also the Cartans, so the currents related to the bosons we are decompactifying, that are massless in general, also at finite distance in moduli space, but in an infinite distance limit will have a very important role. In particular, we see that the J's depend also on Z bar, but this contribution to the conformal dimension vanishes in the limit. And moreover, explicitly, we can see that computing correlators and taking this limit of radii going to infinity just selects out the purely holomorphic component. So if we do this, and to read the data of the theory as explained before, we find these formulas. So for instance, from the pairing of the currents given by the Cartan-Killing metric, we can see that there are no, all the components involving the C's are 0. And so in particular, the CJs are orthogonal to all the generators and to themselves. From the structure constant between the J's, we see that these form a loop algebra, but in particular, the fact that there is a non-trivial structure constant involving also the C's shows us that these C's are actually have the role of central extension in this algebra. So to conclude, we see that from the lower dimensional point of view, we recover an algebra which is the affine version of the one we are decompactifying to, where the central extensions are given by the bosons we decompactify. And in particular, this identification means that in all, if the algebra is semi-simple, so as more than one simple factor, all of them are actually made affine by the same set of central extensions. So just to be concrete, we can consider the case of heterotic on S1 in the decompactification to E8 times E8. Since this is just a warm-up, this is for the thing I will say in the following. We know that we could actually decompactify also to the SO32 theory, but I will not consider it here just because it has no analog in the CHL case, and so I will focus on E8 times E8. So from what I said before, I could just basically copy-paste the algebra and just say that in the limit we recover E9 plus E9, but let me do like a kind of small exercise that will be needed in the following. In the sense, let me consider, like, differentiate explicitly the two copies of E8, where the JA are the currents under the first EA, and the J primes are the currents of the E8 primes. And let me call K and F the Cartan-Killing metric and the structure constants of one single E8. Here I'm not making them different, because while the currents have a different expressions in terms of the heterotic fields, actually the structure constants are just the same, and so I will just consider them with this common notation. We can then change the basis of our 10-dimensional E8 plus E8 algebra in the basis of symmetric and antisymmetric currents, where the antisymmetric currents is denoted by where the like has this index a dot. And it turns out that the JA pluses generate an E8 at level 2 on the worksheet, while the J dot are in an adjoint representation of this E8 at level 2. And then, if we look at it from the 9-dimensional perspective, we still see that the asymptotic currents are the momentum tower of this set, plus the boson associated to the circle direction, which I call Y. And then the algebra that we know is E9 plus E9 gets this form, which will be useful for us in order to compare with the CHL case. So let me just briefly review what all this CHL string is about. So it this was Chowdhury, Hockey, and Liken were the first one presenting it in the fermionic formulation of the heterotic string. But let me follow the presentation of Chowdhury and Polchinski that instead they used the bosonic version. And they build the CHL string as a Z2 freely acting orbifold of the E8 times E8 heterotic theory on S1 that acts as follows. So if we have our, let's say, S1 with radius R, let's say that the associated field is given by Y, and then the E8 times C8 prime bosons are respectively X and X prime. Then this orbifold action consists in the exchange of the two E8 factors accompanied by half a shift along the circle. This is a symmetry of the heterotic theory in the case of symmetric Wilson line, so I will restrict to this component of the subspace of the moduli space. As far as the action on the Hilbert space is concerned, so a state in the heterotic theory is labeled by momentum and winding along the circle and by heterotic momenta. And under this orbifold action, the two heterotic momenta of the first and second E8 factor are exchanged, and then the shift on the circle gives this phase dependent on the momentum. In particular, the Hilbert space of the theory has an untwisted sector given by the states heterotic states that are invariant under this orbifold, which has integer winding, and one twisted sector where the states have twisted boundary conditions, and due to the half shift on the circle, the winding turns out to be half integer. So the fact that we did this orbifold in 9 dimensions and we didn't just consider the exchange of the E8 factors in 10 actually has a fundamental importance, because just the exchange orbifold produces a theory which is equivalent to the original one, as can be seen, for instance, by computing the partition functions. While the shift on the circle leads to rank reduction. And in particular, if we consider an additionally compactify the theory on a torus in such a way that the number of internal dimension is D, if in the heterotic case we have 16 plus D rank theory, in the CHL case the rank is only 8 plus D. And in particular, also the moduli space is different and is just given by OD D plus 8 over the maximally compact subgroup up to the T-duality action. But apart from this, all the symmetry enhancement business works the same way. So at the generic point in the CHL moduli space, the symmetry is given by the U1 to the D plus 8. Well, at special loci in the moduli space, there are symmetry enhancement that in this case involve currents that can be both twisted and untwisted. In particular, let me give you an example that can also show how the rank reduction works. So let me focus in 9 dimensions with generic radius and no Wilson line. Here the gauge symmetry is shown to be E8 at level 2 on the worksheet plus U1. So the U1 is related to the S1 boson, while the E8 at level 2 is constructed as follows. So we can still work in the plus minus basis for the currents of the E8, and then we see that the plus currents are invariant under the orbifold and then are preserved, while the J minus are projected out. And so this E8 at level 2 is exactly generated by the JA plus, as one can show that there are no twisted currents in this locus of moduli space. So now we could ask the same question, namely, what happens if we try to decompactify the theory? So it is known that actually there is only one decompactification limit that can happen up to T dualities, which is the one to the 10-dimensional E8 times E8 string, because due to the structure of the charge lattice, the limit to SO32 decompactification is forbidden. And so one can still look at the massless states in the limit, so the asymptotic currents, let's say. Since all the twisted states have at least half a unit of winding, they turn out to be infinitely massive in the limit, and so all the states that may become massless are actually in the untwisted sector. So the first class of those is the even momentum towers of the E8 at level 2 currents of the J pluses, which if I write the momentum as 2n are labeled by an integer n. So these m equals 0 are the states that correspond to these J's with n equals 0, and then there is the whole tower of states that are massive at the generic radius and then become massless in the limit. But then this is not enough to recover actually the full E8 times E8 as we would expect, because the rank is just 9, so it's just 8 in this case, sorry. But actually there are additional currents that become conserved in the limit that are the hot momentum towers of the antisymmetric current in such a way that the orbifold charge is just +1. And if we want to keep the notation like 2r to be the momentum, this can be labeled by a half integer. So we see that this corresponds to states that are still in the spectrum of the theory, but that are massive at generic radius. And then taking the limit r going to infinity, just like give an additional tower of states that if we integrate in, just gives back the full E8 times E8 algebra. And in particular, there is also the additional circle boson that becomes massless. And of course, it also has like a whole momentum tower, but in this case, it doesn't contribute, as was the case for the heterotic. This doesn't contribute to the current algebra, and so I will forget about it. And still, we can do the same trick as before, so compute the correlators, which will turn again out to be completely purely holomorphic. And by doing this and taking the limit of r going to infinity, this is the data that we find, where f ABCs are the structure constants of E8, and we chose like a basis where the Cartan-Killing metric is just diagonal. So, I mean, this is not particularly illuminating, I guess. So what we could do is try to compare with the heterotic case, the decompactification from 9 to 10 dimensions. So these are the current, and this is the E9 times E9. We see that the structure is similar in the sense that still the two algebras depend on the data of E8 times E8, essentially, and then we have this loop structure, and that the Y act as a central extension. But we have two main differences. So the first one is the fact that the central extension part has this additional factor of 2. So this is not surprising in the sense that the geometry of the CHL string just gives a circle which naturally has the radius which is half the heterotic one. So these two can just be reabsorbed in the redefinition of Y. But there is a structural difference, which is the fact that the antisymmetric currents are labeled by half integers and not integers. And this turns out to be the structure of what is called twisted algebra, which is basically what we get from an affine algebra by applying an automorphism to the finite algebra generating the full affine version. When the automorphism is an inner one, then the two theories can be shown to be equivalent, but this is the case of an outer automorphism, these are different and they cannot just be mapped one to the other one just by a change of basis or some field redefinition. And so the result is that this corresponds to an E9 plus E9 twisted affine algebra. Moreover, it is important to stress that the fact that we are in 9 dimensions and we are performing the shift on the circle is actually of fundamental importance because, okay, here we missed the... Okay, let me show like this. The fact that the shift is very important because if we were just to exchange the two E8 factors, then the structure of the currents would be like the heterotic one. The only difference would be that this JA dot would be in the twisted sector of the theory, but they would still be in the joint representation of the E8 at level 2 J pluses, and they would have the same OPs with the J pluses and among themselves. And in particular, the fact that there is no shift on the circle would imply that on the Hilbert space, the action doesn't involve any phase. And so still the full momentum and winding towers would be allowed so that we would recover actually the full, like the untwisted E9 plus E9 algebra. So let me conclude. So we looked at the decompactification of the CHL string to 9 dimensions to the E8 times E8 10-dimensional theory. And here, the non-trivial effect of the CHL orbifold in 9 dimensions can be seen in the fact that the algebra that arises in the limit is a twisted version of the E9 plus E9 one that we find in the heterotic case. In particular, if we were to further compactify on a torus this theory, decompactifying the torus cycles that are not associated with the shift would just give a normal affine untwisted algebra, while decompactifying the CHL cycle would give a twisted version of it. So in particular, we could answer our question in the sense that the algebras that arise in the decompactification limit are somehow non-universal in the sense that even if the final theory we reach in the decompactification limit is the same, the structure of the algebra itself depends on the component of the moduli space that we start with. Thank you.
Thank you, Veronica, for the nice talk. Are there any questions? Hector has a question.
Hey, thanks for the nice talk. Did you think about the compactification of the SO32 on a torus without vector structure? Like, if you put the theory on that torus, and then you would have like a symplectic group, and you can also think about the decompactification limit in this time from 8 to 9 dimensions.
Okay.
And personally, there should be a similar structure. But I don't know if you thought about it.
No, I didn't honestly, but yeah, I mean, it's plausible that the structure could be the same.
Thanks.
Any further questions? I maybe have a quick one. So you probably said it already, but Like you got either this normal algebra or the twisted version. Was there a natural way to understand this from the orbifold that you were doing, or?
The twisted version.
Mhm.
Yeah, I mean, the fact that we have this automorphism is basically what defines what a twisted algebra is, in the sense that it comes from the untwisted one when we perform this some automorphism to the finite component, like the horizontal algebra of the affine one. And so this is like this naturally comes out of it.
Okay, I see. Thank you. Any further last questions? If not, then let's thank Veronica again.